Wednesday evening, we are going to talk about an interesting paper, which questions whether uh, some emergent abilities observed in large language models, they were a mirage. So that obviously begs the question, well, when were these emergent abilities noticed? What are these emergent abilities? And what is the relevance of all of this? So I'll go through a little bit of a background on this topic, and then we'll launch into this paper. Keep going the fact that we have relatively low attendance. I was requested not to do any very technical paper during this holiday season. One of the more technical papers are coming up next week, and then we'll have Mamba and so forth coming the week after that. But today is a relatively, it's a very important paper, but I believe it'll be an easy read for all of us. So a bit of a background. What is emergence? Emergence, the topic, the word sort of has been around in physics for quite some time. And what it says, I suppose, a very qualitative way of saying it is the way Aristotle said it, when he said that there are situations when the whole is more than the sum of parts. Right? So examples that are given is that sometimes in the sky, you see these formations of birds. They make these beautiful patterns as a flock, right? And they show this behavior that if a predator comes, they change their shape in an optimal way and so forth. And yet each of the bird is doing whatever is a local activity. The sum total of all of those activities leads to a behavior that you wouldn't have been able to predict simply by observing the dynamic of the individual birds. Likewise, a phase transition in materials is a classic example. If you study the molecules of water, you can study it in terms of its kinetic energy, in terms of its motion, and so on and so forth. And yet, as you lower the temperature, you notice that it goes through a phase transition, and suddenly it forms these beautiful crystals, ice crystals. Or if the circumstances are right, it might form these beautiful fractal shapes, the snowflakes. And so these things are emergent. Right? Many of you would say, if I heat up the water, it becomes steam. Yes, it does become steam. But from that, can you conclude that it will go up and become these beautiful clouds in the sky? Right? So all of this points to a pattern that has been studied in physics for quite some time, that of emergence. They're emergent behaviors or emergent phenomenon. And I believe the classic work or the essay that was written was essay by Anderson, if I'm right, in 1972, called, I believe the title was, and please forgive me, somebody, one of you, if you're researching it, please post it in the chat what the exact title is. But if I remember, it used to be Emergence, Bigger is Different, or something like that, right? Or like at least to something different. As you increase the scale of something, it all adds up to more than what you expected. Right? So that is emergent behavior or emergent patterns or things like that. Now, when it comes to large language models, and there's a little bit of a background that is interesting. People have been observing for some time that, I mean, let's rewind back to the transformer. When the transformers came about, you could scale these transformers to a pretty large extent, at least when you contrast that to what was before transformers for natural language. For example, you had RNNs. RNNs were not really things that you could scale very much. But transformers could be scaled, especially they could use the GPUs, the math coprocessors in the machines, very, very efficiently, right? And just as a very quick recap of a transformer is that you could do, one second. You could do, let's say, you could have multi-head attention. So suppose you have a sequence of tokens T0 to TN tokens, then what you could do is it would go through, after the embeddings, etc., are done, embeddings, token embedding plus position embedding and all the usual stuff, it would go through a attention head, and this is attention head internally would have your, and this is a very basic recap. It would have your standard softmax, k dot, suppose you have a query vector, k dot q, right? And I'm again being very sloppy because we in the community sort of know this. We all are familiar with this literature. But just think about it is that the main idea is that this is the attention equation. It would go through attention, followed by, and there would be obviously some residual connections, but finally there would be feed forward networks, and it would come out. But then the interesting thing about attention is that you could scale it up in two different ways. One is through multi-head attention. So you could have other mirrors of these attention heads. So you could create this literal towers of them. 1 tower, 2 tower, 3 tower, 4 tower, and so forth. And then the output of this goes to another attention head, goes to another attention head. So you could vertically stack the attention heads so that the output of one goes to the input of the other. And then you could have this towers of attention heads in parallel, these parallel towers. So that was the multi-head concept. So transformers brought about a highly, in some sense, a parallelized architecture. One of the interesting things that this parallelization did, and I'll put it in a way that is interesting to think. If you go back to the original paper, or the work of Jeffrey Hinton, when he was talking about a mixture of experts, which we covered last time. A mixture of experts, I'm not talking of the sparse mixture of experts, where you deliberately bring down the number of parameters at inference time, at compute time, forward compute time, because you pick only one of the experts to do the job. But if you really think about it, these multi-heads, they behave like separate experts. One would catch on to the grammatical aspects of it, of the tokens. Another would pick up on some other linguistic aspect. Each of the multi-head towers would latch onto a different, it would see a different aspect of the reality, of the input reality, and learn to capitalize on that particular reality. Right. And so you can imagine that as you build more and more of these towers and deeper towers, right? Obviously, that would be a very structured way of increasing the number of parameters in the transformer architecture. And both in the encoder and the decoder, or whether you just use encoder or you just use pure decoder architecture, it doesn't matter. Whichever way you look at the transformer, one of the things that it gave is an ability to massively scale it up. And when people started scaling these, they started observing, and this is way back in 2020. Remember, it's been a couple of years since the transformers came out at that particular moment. And what people started observing is something remarkable, actually. And much of it is captured. Perhaps it's worth reading through the introduction. I'll read the introduction here. We said, we study empirical scaling laws for large language model language model performance on the cross entropy laws. Cross entropy loss is a very typical, like if you're using a classifier or whether you're predicting a word. Now, if this word should have come out or some other word should have come out. So cross entropy loss and its close cousin, negative log likelihood, are the usual suspects implicated when you talk about these transforms, LLM, especially in the LLM context. So we'll take that. So I'll repeat the sentence. We study empirical scaling laws for language model performance on the cross entropy laws. The law scales as a power law with model size, data set size, and the amount of compute used in the training. So please observe the use of the word uses a power law. Now, when you use the word power law to, especially to physicists and in the technical community, it does have a specific meaning. So what it says is that the law scales has a relationship, a power law relationship to all three of them, to model size, to data set size, and to the amount of compute. Like, just think how many GPUs you have, essentially, compute size, compute capacity. Let me just say, compute capacity during training. So now the question is, what is a power law? A power law is that the loss. So I will just speak in this context, I'll just speak of that. See, suppose you have a function, y. It is some function of 1 over x, or some constant over x. Let's just say c over x to the power k, right? So let's take the very simple one. K is equal to 1, c is equal to 1. So y is 1 over x. So what will this look like? It will, if you say, when x is close to 0, this value will be close to infinity, and then it will show this classic behavior, isn't it? It will asymptotically, as x increases, y will tend to 0, right? Now, if you k, so this is your k is equal to 1. If you make k is equal to 2, right? So let's say if you make k is equal to 2, it will be even more dramatic, like this, right? K is equal to 2, right? Conversely, if you take, let's say, k is equal to a half, it may be a little bit like that. Let's say k is equal to a half, 0.5. Are we seeing that? Right. So the point is that it should be this, c over x, right, to the power k being greater than 0. Or you can write this equation conversely as the opposite of it. You can say it's a relationship of x over c to the power, let me just call it alpha. Alpha by definition is minus k, right? Now alpha has to be less than 0. If k is greater than 0, then you would agree that alpha should be less than 0. It's another way. And in the paper that we will talk about, I believe this paper or in the subsequent papers, you'll see that the computer science community tends to prefer this notation. Right. So what it says is that you have a power law relationship between loss. Now, what is y here? In our context for large language models, y is the loss function. And just to pin it down to a concrete example, think of a cross entropy loss. Are we together, guys? Cross entropy loss. Or if it helps you, just think negative likelihood loss, right? And what is the x here? X is one of these three things. Either the model size, data set size. Model size means number of parameters, which is a good proxy for model size. Number of parameters, which is number of weights and biases in your model, right? And or data set size, how much data it has been trained in, right? Or how much compute capacity you have. So let's go and think about the second and the third part. See, we know that if you train any model, like if you take a very big model that has a lot of parameters and you don't train it with enough data, what will it do? It will overfit it. It will just go memorize it. Yeah. Isn't it? It will just, increasing the data set size has a regularizing effect. It's the simplest regularization you can do of a model, right? And so you do expect the loss to go down as you scale up the data set size, right? So data set size is essentially a no-brainer in some sense. So, I mean, at some point it will asymptote, right? When you're really freed up, regularize it as much as you can, and you have reached the capacity of the model, right? So for example, if you make a polynomial, just to make it trivialize it and go down to something very simple, if you're looking at a polynomial regression equation of just the third degree, then beyond a certain number of data points, I don't think that going from 1 million to 10 million data points is really going to make your model any better, right? Because it has saturated, it has, the loss function has raised the asymptote at that particular moment. Isn't it? But usually with large language models, the general feeling is that these models have become so bizarrely big that we are, and more, in fact, in the recent months, if the experience it speaks of something, it speaks to the fact that people have really not trained the model enough with enough data. So enough regularization of the model has not come through. In fact, I mean, this is a bit of a digression, but one of the realizations that somebody has, somebody gave me a topic. It must be the title of a paper, or was it an article or something? Somebody says, textbooks is all you need, right? What the person was referring to, I suppose, as a spin on the word attention is all you need. What we're saying is that textbooks are really high quality data. And so when you train a LLM with really high quality data, then you get much better result than the junk we train it with, the web scrape junk we train it with. The other thing that people have realized is that and then, I mean, obviously there's a lot of this. There was the Google paper, and if I'm right, I'm referring to the one that talked about the chinchilla optimal and so on and so forth. Basically, they found that we are all getting carried away with the fashionable. It's become far more fashionable to create bigger and bigger models at the expense of training it with more data. So what happens is that we have so much hardware. We can either do more and more epochs over larger data sets, or we can just make bigger models. So generally, and in fact, this is one of the things I believe this paper will go into. Oh, no, not this paper. The other one, the Google paper goes into the chinchilla and all of that, is that you should scale both. It's common sense. You make the model bigger, get more data. That used to be common sense in machine learning if you were doing simpler models. But in a way, I suppose a lot of empirical results had to be brought in to convince people that don't just go make your models bigger. Just bring more data also along with it to do that. So that's a data set size aspect of it. Now, the third is compute capacity. That's a no-brainer, because the more compute you throw at it, compute for a given data set size, for a given model size, what will compute capacity give you? Well, if nothing else, it will give you more epochs, isn't it? It will give you more chances of doing hyperparameter tuning, isn't it? And it will give you more chances of searching through the hyperparameter space for the optimal things. And therefore, you'll have a better loss function, the better asymptotes. Once again, a no-brainer. Right. So what we'll do is, instead of dealing with all three of them, we'll just take the first one as a proxy for all of them. Right. In the discussion that we're going to do, we are going to say model size. And model size, one very sort of a rough and ready proxy that we'll take is just the number of parameters. And that seems to be the big deal these days, right? I have a 7 billion parameter model. Is that? Oh, so lame. I have a 70 billion parameter model. Oh, is that it? We have a 1.3 trillion parameter model. That seems to be the big thing going around these days, right? So this one talks about things like that. And obviously, see, these things have a lot of practical implications. Most of us who are into AI, we do look at our budget and then go buy a 4090, right? And then immediately NVIDIA stock goes up. Right, but we all are sitting up on 4090, and the first thing we do is we bring it home and then we start playing around with models. And the first, and to develop the sad realization that $2,000 later, we can only run baby models, isn't it? Or quantized models, 8-bit quantized, 4-bit quantized. And there's a joke now, there's 1-bit quantized or something. Or something bit quantized. So we just get to play with it. Right? So compute capacity and these things have very real effects, and model sizes have very real effects. So I will stop this paper at this, because this is not a point, but I suppose it speaks to that. If you look at so now the point that I want to raise is, look at this equation. And if you take the log of this equation, log y, and let me first convert it to loss. So this equation in our language is loss is proportional to the number of parameters. X will take the size of the model divided by C with some alpha being smaller than 0. Actually, I never like this notation. I like to always think of it the other way around, some constant over n, k being greater than 0, k greater than 0, because that is how physicists typically think of power laws, reciprocal laws. The power law is a reciprocal power law, isn't it? Loss decreases the more you increase n. It's a reciprocal relationship. So we take this. Now you have this relationship. Let's take the log of both sides, log of L, and by that, of course, I mean natural log. will now be k times log of c minus k times log of n, isn't it? So now this is a constant, we can forget about it. And so you could say that ln of loss is approximately proportional to negative k ln of n. So now, if you look at this quantity as your new y, let me call it y prime, and this quantity as your new x prime, would you say that x prime is basically minus k times x? So, right, it's an equation that will look like, it will look like this, isn't it? Log ln L and ln, in this particular case, ln n, right? And so what you can do is you can look at it as powers of 10, 10 to the 0, 10 to the 1, etc., etc. And by the time you reach here, well, of course, 10 to the minus 9. So it is, of course, looking at the reverse scale, and it is going along in this direction. What is the loss? So you would imagine a relationship like this. Actually, when I look at the scale of these numbers, I find this in terms of compute capacity. I just look at it in the number of parameters. So see, guys, this is a trillion. No, billion. It's a billion, isn't it? 10 to the 9 is a billion, right? Oh, sorry. I should zoom in. Okay, let me go to the touch enablement. Touch on. Okay, let's see. Yeah, let's look at this now. Is it more legible? Right? So you see that 10 to the 9 is, as I remember, it's a billion. Today, you would rather frown upon it. Just a billion. We now go trillion. But okay, the same relationship holds. It's 2023 is a different world. But the point is that, as you can see, the loss decays, isn't it? Linearly, log loss decays linearly with the number of parameters. Right. And well, the way the x-axis has been parameterized, it's a little bit misleading because it is written as 10 to the 5, but in reality, we are talking about, well, yeah, this is a log of 10 to the rather. So that's that. So this is one thing I found a little bit. It took me a little while to realize that the way they have written it is a little bit misleading, the way the graph is done. Or at least I found it. This is it. So this is the point that this paper is making. They discovered that the loss decreases. So this is an argument in favor of saying, hey, let's bring in more and more data. Let's bring in more and more GPUs. Let's go and bring in more and more, make bigger transformers. Bigger is better, isn't it? Bigger. And the end, like I suppose, message from this paper is bigger is better. Right, that's all. So we'll leave it as that. And let's go back and now go to the next paper, which, so there's more. Now the question is, there was in between a paper that Google, which went into things like, what is the optimal way to scale up? So people were just doubling the model size. And what that paper said is that, I think I have the name of the paper. It should be somewhere here in my pile of papers. Guys, please give me 1 sec. My daughter is at the airport. So the paper was, let me give the name. Yeah. So there is a paper which is called Training Compute Optimal Large Language Models. In other words, it's a Google paper that basically says, how should you go about it? And well, not just Google, there are many authors. So basic thing it says is that don't just scale the model, scale the data set also. You would consider that, like, see, if you don't come from the just pure LLM world, like if you didn't just wake up and thought that machine learning is just LLM, which the new generation seems to think, right? Well, we have always known that. If you build a more complicated model, go get more data along with it. And a similar thing that the paper sort of says about it. Then came an interesting result, which I will talk about, which is, are you guys able to see it on the screen now? It observed It took, if you look at the number of people here on the paper, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 researchers discovered something quite remarkable about large language models. Remember, we talked about the phenomenon of emergence in the physical world. And they started noticing that there was a similar emergent abilities of large language models. And it became sort of a established thing that these things happen. These things do happen. Now, and that sets the stage for our main paper today, which says that these emergent abilities may be a mirage or are a mirage. Now, which of these two statements are true? Are they emergent abilities or are they just a mirage? And the interesting thing is, the way I look at it, and people interpret it differently, but I look at it and say, both of them are true. Right? Depends upon which lens you're looking at it from. Right? So, but let's quickly go through this paper a little bit, and we'll read the abstract. I don't think I finished reading the previous abstract, but we'll skip it. Scaling up large language models has been shown to predictably improve performance and sample efficiency on a wide range of downstream tasks. This paper instead discusses an unpredictable phenomenon that we refer to as emergent abilities of large language models. We consider an ability to be emergent if it is not present in smaller models, but is present in larger models. Thus, emergent abilities cannot be predicted simply by extrapolating the performance of smaller models. The existence of such emergence raises the question of whether additional scaling could potentially further expand the range of capabilities of large language models. Right? So the thinking behind it is that people woke up one day and realized that, oh my goodness, we never thought language models could do arithmetic. And holy cow, it's doing arithmetic, right, at a certain scale. And remarkably, at a certain scale, it seems to have started doing arithmetic pretty well. Right. So, and this is empirically established. So there are emergent abilities, right? So that statement is true, and we'll go a little bit into it. And as I said, I will take the position that this thing and its the subsequent paper are both right in their way. So it goes on to say, and interestingly, it does refer to that paper. If you look at it, it does talk about, where did my paper go? Remember, it again refers to that physicist's paper, 1972. Emergence is when quantitative changes in a system result in qualitative change in behavior. Well, that's quite a mouthful. In simple terms, if I decrease the temperature just a little bit, I didn't quite expect water to just become a cooler water, but instead it has become snowflake. You see that, right? There's some emergent phenomenon that is, there's a phase transition, for example, right? So that is it. That's what it's talking about. That's as an illustration of that. Here we'll explore emergence with respect to model scale as measured by training. Specifically, we define emergent abilities of large language models, this particular sentence, as abilities that are not present in smaller models and cannot be predicted. Like, for example, if you look at the loss function, it was not possible to predict that suddenly it will start doing arithmetic correctly, right? And you see that. So they define it. In this paper, we'll consider a focused definition of emergent abilities of large language model. An ability is emergent if it is not present in smaller models, but is present in larger models. Make sense? It's a pretty crisp definition. And I suppose I wouldn't go too much into this picture, but the earliest things they observed it in, which is pretty legit. Let's look at this particular prompting. They show prompting. Is it? You give it. So we all, by now, this was written long ago, but today, when was this paper written? I think it is 2022. Doesn't that feel like ancient history now? Okay, so There we go. So this points out that well, today we have become pretty clever at prompting, but at that time, you would give it an input. You said, this movie sucks. It's an example. Sentiment is negative. I love this movie. Sentiment is what? Right. It should say positive. You give it to the language model. And what they found is that you give it to a small language model, right? And it would be like, I don't know, right? Positive, negative, random answers. It wouldn't come up with the right answer. But as you scale the model up, and obviously you pre-trained it, and then you gave this example. For example, if you did that to something like Cloud or ChatGPT or Bard, they would scoff at it. It's too easy. They would all come with the right answer, isn't it? GPT-4 and all of them would immediately give you the right answer. So these are ginormous models. So we know that this is a fact, right? So there is an emergent ability. Smaller models can't do it. Larger models can do it. But it isn't that they can't do it, but that ability is sort of, as you scale up the model size, it sort of abruptly shows, right? That is their key observation. Just like you cool water, right? Normal room temperature water, keep cooling, it just becomes colder and colder and colder. It's still water. And then suddenly it becomes ice, right? It's a completely different thing that comes out of it. In a similar way, a model couldn't do this, couldn't do this, couldn't do this. Oh my God, now it's able to do it as you make it bigger. That's the key observation. So it goes through many of these, and I don't believe it's terribly important what these metrics are, but the important thing to do is, if you look at it, do you notice that they have looked at accuracy as a metric to do this, and exact match. If you ask it to predict a certain string, accuracy, and this is something that the subsequent paper will latch on to. Now, what was not so clear at that time, or in hindsight, so we all read this paper and we were all duly impressed, and we were all like walking around, oh my God, large language models have emergent abilities, so amazing, right? But it turns out in hindsight, obviously things look much clearer. There was something interesting about these metrics. These are what the subsequent paper said, rather discrete measures of accuracy. So for example, if I give you a multiple choice question, right? Accuracy means out of the 5 choices, did you pick exactly the correct one? What if the correct one in your logics was the second most probable answer? Well, your model did come pretty close, right? Right. That's right. It came pretty close. If you had looked at the top 2 answers, then it might have qualified, isn't it? And so what the subsequent paper will do is point out that maybe the emergent abilities had something to do with the kinds of metric you picked to do this analysis. And so, but let us go with accuracy, because see, you may say that accuracy is a discrete measure, but it is of practical value if you give multiple choice questions. In GRE, if you come up with a second best answer, you still get a 0, right? Or SAT or whatever it is. And you have all learned through hard experience, isn't it? So therefore, accuracy is a practical, valuable measure, discrete or not. And so if you look at these discrete measures, then there is emergent behavior. Larger models are able to crack GRE or SAT much better than smaller models can, right? Smaller models will fail. And we know that, right? These bigger and bigger models, they seem to be outdoing every single competitive exams, and smaller models cannot. So to that extent, there is emergent behavior, right? Exact string match. So suppose you have to produce a sentence, 5 token or 10 token sentence. Exactly that. What if 9 of the tokens matched out of 10? Right? And could you have observed that as you scale the model up, in the beginning, nothing, there was 0 match, and gradually the average number of matches was 1. The average number of matches went to 2, 3, 4, 5, 6, 7, 8, 9, and then finally 10. But when you do exact match, no, it's a winner take all, right? It's basically you either get it absolutely right or you're done. It's wrong. Right? So there what happens is, once again, you observe some emergent behavior. And this paper went on to do that. But there was something I liked about this paper, which was that it sort of had some sense of idea where at somewhere I noticed that it was actually quite prescient about it. It did talk that if you look at cross entropy, one of the continuous measures, then it was slightly different. I don't know where it was. I like that paragraph in this paper. Somewhere it was. Okay, we'll skip it because we have to go to the main paper. Yeah, in a moment. But it is there. It isn't that these people were completely oblivious of it. I think they were beginning to get a sense that, oh, by the way, if we take this other metric, then the emergence is not as pronounced or something like that. Right. And then, of course, one nice thing is we live in the world in which the big question is, what risk does AI pose? And if these things have emergent abilities, I suppose the unstated, a very kindergarten version of it is, will the next emergent ability would be, let's chop off everybody's heads, right? Or something like that. I don't know, I'm just kidding, right? Off with the heads. So anyway, there are risks, attendant risk, and things that you need to worry about. And
I
go
do
ahead.
have a question. So do they speak about how the quantization affects these emergent abilities?
No, they don't speak about quantization. At least I didn't see it.
Okay.
Quantization in particular. See, quantization is to a large extent the pastime of open source, right? When these guys with Google, right? What's 1,000 GPUs here or there lying around on the floor? So I rarely see these big guys get too much into the quantization aspect, at least way back when, right? Quantization has become a much more recent thing.
Got it.
So
Also, I'm wondering, how would a 70 billion 16-bit model perform compared to 70 billion 32-bit or so? So
that's a very good question. I don't know the answer. She had to look into that.
Yeah.
Look into. But the general belief, the last I checked, was that when you quantize it down to 16-bit, you don't lose much. When you quantize from 16 down to 8-bit, you begin to lose about 10%. When you quantize from 16-bit down to 4-bit, then all bits are off. Basically, you lose quite a bit.
In accuracy and execution was followed.
In accuracy, in every measure. Right? You ask it a question and 4-bit will give you a very short answer. And then it will start hallucinating or doing something like that. I mean, Srinath, we are running it. You are part of the learning community here, right? You know that the inference server, we have the Mistral and the Mixtral both running, the 7 billion model running, right? Using the Llama CPP. Ask Praveen. We have it running on the machine. I believe at port 80, 8,000 or 8080 on the inference server. You can try it out. You'll see that after a little while, you ask it a question, first 3-4 sentences are good. After that, it just wanders off in the wrong direction. And it's a quantized version because there is no way we could have put the whole mixture of experts onto our inference server, even with its 4 GPU.
Yeah.
Right? It's literally that bad. So here's the thing. Let's just say that you are sitting with 1 GPU in your room. I can see your machine, by the way, is still running. And because I can see the flashing lights from it, colorful flashing lights.
Thanks to Sukhpal.
Thanks to Sukhpal, yes. And the inference server has 4 GPUs, but still we are beggars compared to the likes of this big.
I read somewhere that to get good response out of Mixtral, you need 2 A100s. So
you need 2 A100s. That is it. You have to run the model in all its glory without quantization. Yeah. So, Srinath, you don't seem to show any signs of jet lag. Good.
Oh. I didn't travel. I'm here.
All right, so we'll move on to the main paper of today, which is that are emergent abilities of large language models on Mirage. It's a very interesting paper, and obviously you can go and watch the YouTubes. Miranda has given a YouTube talk and so on and so forth, one of the authors. And other authors may also have given talks, I don't know. This came out from Stanford. It basically says that it precisely redefines what emergent abilities are. It says that we will define emergent abilities as something with two properties. And let me go and do that. And then we'll come to the main finding. It says the term emergent abilities was recently and crisply defined as abilities that are not present in smaller models, but are present in largest models. Thus, they cannot be. Now, where did we encounter this sentence? In just the paper we were studying a moment ago. Remember, we highlighted that sentence. Such emergent abilities were first discovered in blah, blah, blah. Let's skip all of that. So these quotations collectively identify two defining properties of emergent abilities in LLMs. First is sharpness. What's the sharpness? There's a sharp elbow. Here, let's look at this. Sharpness, transitioning seems instantly from not present to present. By that, if you think about it, like as you increase the model size, and you think of increasing it as a progression in time, it seems that suddenly it appears, right? The accuracy, which was basically sort of quoting zero, has taken a jump up. Right? Now, one thing to remember, guys, accuracy doesn't just keep climbing. Ultimately, inherently, all accuracy has to asymptote to, if I were to go here, 70, 100. It has to, even if it goes here, ultimately, it has to asymptote to that, right? There is no such thing as continuous thing, but we'll leave that. So abruptness or the sharpness is one thing, and the unpredictability. This is crucial. You can never predict when the thing will appear. Remember that when we made that scaling law, power law diagram, it seems like the law keeps falling down log linearly, right? Now the thing is, how do you put the two together? How do you put the scaling law? How do you juxtapose it with the emergent phenomenon, right? Emergent abilities. So that's the conundrum that this paper addresses. And how does it address? So anyway, it says that, okay, the way people think of emergent abilities is you don't know at what scale it will come. So obviously, if you don't know, then the only thing that you can do is go get bigger and bigger machines and make bigger and bigger models, and then obviously have bigger and bigger data sets. And from what I hear, we have scraped the whole world's data set and it's proving insufficient. So now what people are using is they're using, what is it?
Repetitive.
No, not just repetitive. They're using LLMs to produce more data, synthesize more data to train larger, smaller LLM. But not only that, the state-of-the-art LLMs to generate a lot of data to produce an even bigger LLM.
Isn't that wrong approach?
It is, in my view, it's wrong because it may reinforce all the biases.
Yeah.
Right. So, but they just need more data. They're trying every trick under the sun to take existing data, synthesize data, everything goes, right? If only we can train even bigger models, that seems to be the game, right? The only alternative is the approach that we talked about last time, the mixture of experts, right? Sparse mixture of experts. So anyway, we look at this. So now these emergent abilities have garnered significant interest, blah, blah, blah. We know that. I'll skip all of that. I'm assuming that you guys have like sort of read this paper. And so I'll just focus on the main thing. And this is it. So I'll read this paragraph because this is interesting. In this paper, we call into question the claim that LLMs possess emergent abilities, by which we specifically mean sharp and unpredictable changes in model outputs as a function of model scale on specific tasks. Our doubt stems from the observation that emergent abilities seem to appear only under metrics that non-linearly or discontinuously scale any model's per token error rate. That statement, I've highlighted it, but I would like to again underline it too, because this is the main thing this paper says. It says that the emergent abilities seem to appear only under metrics that non-linearly or discontinuously scale any models per token error rate. Right? So see, it is producing token after token. That's what LLMs do. If you look at the amortized error rate per token, that is one thing. But when you say that, no, I want to look at the correctness of the answer, accuracy, multiple choice. Now you're not doing per token. You're saying the whole is right or wrong. So it's a very discontinuous and nonlinear way metric there, right? Or exact string match. You may have produced 50 tokens, but either they all match exactly or they don't, which is very different from saying of all the tokens that were generated, what proportion of tokens were correct, isn't it? And so it gives an example that we show that 92% of emergent abilities on the big bench, by the way, big bench was a benchmark used in the previous paper, appear under one of these two metrics. Basically, vast majority of them. Multiple choice or exact string match. Both of them. Yeah. And so they raise this question. This raises the possibility of an alternate. So they're saying that maybe these emergent abilities are not characteristics of model and scale, but an artifact of the metric you are using. Now, if that statement is true, then you have to show that if you use a more continuous metric, then you don't have an abrupt emergent ability. You'll have a more gradual emergence, right? You would see a more gradual emergence. And that is the gist of what it is doing. And it says that, see, look here. There's a bit of mathematics we'll go through, which is very easy, but I will just go through the diagrams a little bit. And this diagram is crucial. So let me have it fill up the whole screen. This line we are familiar with. Look at the line A. Let's look at this diagram, for example. This is what we encountered in the scaling paper, right? Scale the model up, your cross entropy loss per token will go down. Makes sense, right? Linearly goes down. Now, if that is true, what is the probability that a single token is correct? That is obvious. So we can do a little bit of arithmetic here. Let's do that. Let's say that your loss was log probability, right? You remember negative loss probability of a given token. I think they use the word V, so I'll also use the word V for that particular token or something like that, right? So a probability of producing that answer. Guys, this is your standard cross entropy or the negative log loss thing. So if this is true, and P is the probability of producing the right token, right? The right token. So you would agree that I can inverse this and I can say PB is equal to e to the minus log, right? L. Isn't it? E to the minus, e to the, what would I do? E to the minus L. Make sense? Right. So if this is true, exponential. So yeah, this is it. Yeah, I got it right. That is what this guy is saying here. It makes sense, right? And remember that the loss is a function of the number of parameters of the model, how big your model is. So then if you just plot it, it's just theoretical plot, no mischief here. It will take a shape like this because this is just the inverse of this. The probability, I'm putting it here. It is a B follows from A, guys. It is still theoretical. There's no actual empirical thing here. Not only that, see, if you really think about this, probabilities can go from 0 to 1, isn't it? So what is not implicit here is, I suppose, that this will ultimately asymptote, and this will asymptote here, isn't it? And it has to, right? It has to, but it will. So in other words, now from this, the emergent abilities, now what happens is, suppose I take that you must have, what's the probability that not one token, but let's say 5 tokens are all correct? Means first token has to be correct, second has to be correct, third has to be correct, fourth, 5. So let's say 5. So it means that I need to take the 5th power of this. Suppose I take the 5th power of this, you get this picture, right? It turns out, think about it this way. This is your curve. So hang on. Here's a basic intuition. If I say y is linear in x, well, this is not exactly linear, but let me take it linear. Y is proportional to x. Then if I say y is proportional to x square, what does it do? X square looks like this. X cube looks like this. Now, do you realize that it begins to look like this? And does this curve now begin to look like, actually, let me remove this and point out, and this is a very simple mathematical, oops, sorry, this is way too broad. What should I use? Let me use this color. Forgive me for my, well, I just completely destroyed the actual data, but too fat. Okay, too fat. Let me humor me for a moment. So do you notice that this is exactly what a quadrant, like a y is equal to x to the n thing would look if you take some semi-straight line relationship and you go on multiplying it by itself, x square, x cube, x 5x, whatever, where x being this being your x, right? What will happen? It will go up like this. When it goes up like this, does it develop a very sharp elbow here, somewhere here? Isn't it? And then you sit up and say, wow, we are looking at an emergent ability, aren't we? Right. So now they're saying, is it possible that that is what is happening? Right? We have just fooled ourselves into a sense that they're emergent abilities, whereas in reality, it's just very basic basic mathematics. Right? The whole nature of your metric is such that you better see it if you believe in the scaling laws. Right? And that is the main point that it is making. That's all it is making. Right? And so you will see, on the other hand, if you say, let's count the number of tokens that were right, then you won't see linear ability, because then you're not doing additive. See, suppose, so let's take 10 tokens. What's the probability that three of them are right? Well, this is right. 3 out of 10 are right. So that will still show a linear behavior, isn't it? It's basic combinatorics. 6 of them are right or 5 of them are right. You are now scaling it up, right? So you will still see a linear output, right? And similarly, so they're taking, in this case, a multiple choice or whatever it is, and the other one is a Brier score, which is again a continuous measure. You will see a more normal linear growth of a performance. Right? That is, if you get this point, basically this is I would say that this is the main picture and the argument because of which it was rated. I don't know if you know this, in the NeurIPS 2023, that just finished in New Orleans, I believe. This got the best paper award, right? And this is it. This picture says it all in my mind. It literally says it all. It's a very simple argument, isn't it? That's that, right? So, and it's lovely when you can make such a simple argument and dispel the ghosts, right? But see, then it raises the question, is there emergent ability or not? Right? At the end of it, yeah, it's a mirage. I mean, it is probably not as shocking or as, all we can say is we have explained it. But at the same time, hey, if you're taking a SAT or a GRE, where the right answer and only the right answer matters, second best answer doesn't matter, then, well, you below a certain scale, your model will fail. And at a certain scale, your model will get high scores. Right? So there is emergent abilities, but there's an explanation for it. That's the way I would say it. And so emergent abilities is or is not is a function of what metric you take. Right? All those metrics are valid. Discontinuous metrics are also valid based on real life situation, and continuous metrics are also valid. So they make this argument. So exactly the same mathematics. So guys, this, you see this, right? This is it. I would have written it more like, if you remember, I would have written it more like Ln is equal to some constant over n to the power k, k being, reciprocal relationship. I would have written as a k greater than 0, and here they take alpha less than 0. So the relationship is alpha is my k is equal to minus alpha of theirs. I like to think of reciprocal as reciprocal. The rest of it is straightforward. This is your log negative log thing. Yeah. They point out this: if you want all of those tokens to be true, you have to get L. Suppose there are 10. All 10 tokens have to be right. So if the probability is this, you have to multiply. So x squared, x cubed, x to the power 10. Will x to the power 10 will look like this. And here is your emergent ability, basically. Right? Effectively. That I think is the main point they are making. On the other hand, if you take something more like which gives you, let's say, partial credits. You know that in exams in India, at least, when you would solve a tough mathematics problem or a physics problem, and your answer is wrong, the prof would nonetheless give you some partial credit based on how much you got right. That's a more continuous assessment, right? So let's say that partial credits are allowed, and then you realize that this is it, what part of it you got right. It has a more linear relationship. And that's it. The rest of it is just metrics, and they empirically show that blah, 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 that when you go back and revisit those data and use a different metric and redo the experiment, then those emergent abilities sort of disappear. Right. And so you notice that it seems to happen only on very specific metrics, but a vast majority of metrics don't show emergent abilities. They are continuous metrics. That's and the x-axis here is an emergent score. They came up with some way of measuring that. There's an abrupt kink, right, elbow in that. That's it. And I guess
What are some metrics that still show some emerging?
actually, if you use a continuous one, they say that none of them show.
Oh.
Only discontinuous will always show. That's it. Right?
Oh.
So it's a all or nothing. Whenever you have an all or nothing situation, exact string match or things like that, you'll see it. Right? But if you don't have an all or nothing situation, let's see. Look at this. Aggregate score, multiple choice grades, you can see has it. And Rauch Elsam, I have no idea what that is, but I'm assuming that that's some sort of a continuous, again, this all or nothing kind of a approach. So you see that metrics of models pair exhibiting emergent, a very tiny proportion of them actually exhibit emergent behavior, but a vast majority of them. So one of the implications, I suppose, that people asked is that, so were the initial guys cherry picking the metric to have emergent? I don't think so, because those are exceptionally high caliber researchers. They were observing, and I think the emergent abilities is there. In certain situations, those discontinuous metrics make sense, right? Right. So it is there and it is not there. I mean, let's just say that is there, but there's an explanation for it. Right? So that's that. That's the end of this paper. Any questions, guys? I'm done. Let's have a discussion. Let's see the chat question. Shalini, would you like to weigh in on this?
I might have a question.
Mhm.
What kind of new innovations that this paper can result in this year?
See, the value of this paper is that it's not mysterious, because if you believe that they're emergent abilities, it begs the question, gosh, what is causing it? We need to understand. But in a way, the main point of this paper is not to say that emergent abilities are a mirage, but you understand why it happens. Right? It explains that. And so it is of value. And therefore, you don't want to just say, we have no idea, but God knows what new abilities will emerge as we scale the model even more. At least you won't follow that line of thinking. That's what I would say is the significance of this paper.
There was this project last semester we did on LLMs, and it was like we were testing LLMs as a brain of an AI agent. And that has a pretty discrete task. We let the LLMs, different LLMs play blackjack.
Yeah.
Like we tested Vicuna, we tested Menstro, 7 billion, we tested Llama 13 till we went with that. And we tested all the models. And that's I was able to relate to this paper, that it works better when it's like discrete tasks, but the two problems that we faced was hallucination and this thing. Like it was not performing good on a continuous evaluation that we were doing.
Okay, so so we have a person here in the audience, Harsh. who said that they did a project in their research lab, and they confirmed that they are seeing this for discrete. They were seeing behavior like this, but they also saw some hallucination at smaller scales. And but for continuous metrics, they weren't getting any such emergent behavior. Guys, if there are no questions, I will stop the recording and we can have a more informal discussion thereafter.